Okay, next up is kinematics, and then we are done with the physics for the exam. Okay, so kinematics is the equations of motion, and this is about 16% of your. Let's see what we know about kinematics. So first things first is just the equations. These will be given to you. I'm not going to go through the formulas now, just to make sure that you know that VI is the initial velocity in meters per second. Vf is the final velocity, also in meters per second. Then we have x, which is the distance or displacement in meters. Then we have t, time in seconds, and a is your acceleration in meters per second square. Now, just a note here, this is acceleration and the symbol is a. In the previous video, when we were busy with potential energy, we also had an acceleration, but that was the specific acceleration of the Earth when an object is falling. So when an object is falling, we have a constant acceleration, which is 9.8 meters per second square. Okay, but this is when we move up and down. Kinematics and the equations of motions in grade 10 is only horizontal movement. In grade 12, you are going to mix the horizontal and the vertical motion, and then you can just remember about the 9.8. But that is grade 12's problem. There are two more equations that I want to add here, and they also help us to get the definitions of velocity and acceleration. So to determine velocity in another way, we rarely use these equations, but they give us the definition of velocity and acceleration in symbol form in much the same way that we did at circuits with the current and the voltage. Now, if we just look at velocity first, we can see velocity is the change in displacement divided, which is per time. So if we take the formula just as it is over there, we can say that velocity is the change in displacement per time. But a more elegant way is to say that velocity is the rate of change of displacement. So just like when we were busy at circuits and we had the formula for current, current was the rate of flow of current. So the rate of flow of current. So the same as the rate of change of displacement. Now, something that you just need to note here is when I talk about velocity, which is a vector, I use displacement, which is also a vector. Okay. If I change this into the definition of speed, I would use the word distance. So speed is a scalar, it doesn't have direction. So speed is the change in distance per time, or is the rate of change of distance. All right. And then you can use the same almost formula for the definition of velocity to get to the definition of acceleration. So acceleration is the rate of change of velocity. So acceleration, that is a vector, is the change in velocity per time. It comes from this little formula. And a more elegant way is acceleration is the rate of change of velocity. Okay, so that is that. Then I've just spoken about vectors and scalars. So let's just have a look at those. So I just happen to use a yellow highlighter for the vectors and a green highlighter for the scalars. So I'm going to keep going with that. Let's just take the green first. The green will be scalars, and in class I showed you this is the way I remember it. It looks like a little man. Okay, so scalars, and this one is also for time. So an example of a scalar will be time. Time doesn't have a direction. Mass is another one in kilograms. It's just kilograms. No one asks you the direction of the kilograms of your body. Then the ones that we're going to work with obviously is speed and distance. So distance is if I want to go from point A to point B, it will be the true path that I follow to get from A to B. So it's usually longer than displacement, which is a vector. So displacement is a vector and velocity is a vector. And that's another way that I remember it. So these are vectors and velocity is one of them. Something else that we can add to scalars that we've been working with is energy. And one that we briefly touched on when we were busy with the energy video is weight. So that is in newtons. So weight is in newtons. It's the gravitational force of the earth on your body. That's in newtons. And then its friend in the scalar bubble is mass, which is in kilograms. And if we just quickly look at displacement, displacement will be the shortest distance between 2 points. So that's the definition of displacement. It's the shortest distance between 2 points. Okay, if there's anything that I missed, I'll come back and add them later. So let's start with the questions. We're going to do the same as previously. We're going to read through it, make some notes, and then come back and answer them for reals. So the first one is true or false. An object is thrown vertically upwards. Its gravitational potential energy decreases. Okay, this is a copy of the other one, so we can remember what we did at energy. A vector is a small quantity. A scalar is also a small quantity. Okay, so now just let's go back. So with vectors and scalars, the fact that it's a vector only tells me that it has magnitude and direction. So it has a size and it has a direction, where the scalars have magnitude only. So the fact that something is a vector doesn't tell me if it's a big magnitude or a small magnitude. It doesn't tell me anything about the size. The fact that it's a vector or a scalar only tells me, does it have direction or does it not have direction? So just off the bat, this one will be false. A vector quantity is described with a direction and a scalar quantity is described without a direction. That's exactly what I just told you. So this one is true. So a vector has a direction and a scalar does not have a direction. A scalar quantity depends only on the initial and final values of the quantity. Now, if you were with me just now, I actually drew this little picture for you. That answer is false. Displacement, or vectors, depend on the initial and final position or value, where scalars do not. So this one is false. I'll come back again. And then distance is a scalar quantity and displacement is a vector quantity, and that is actually true because we put them in the correct bubble. So displacement is yellow, it's a vector, it has magnitude and direction, where distance is in the green bubble, it only has magnitude. So this one is true. A physical quantity that has both magnitude and direction. Vector, anyone? Here they ask the unit of linear acceleration. So what is the unit of acceleration? That is meters per second square. Okay, then they ask displacement of a body is what kind of a quantity? Yeah, it's a little bit unclear, but they're asking is it a vector or a scalar? And we just saw in the previous question, displacement is a vector. A physical quantity that has magnitude but no direction. That would be a scalar. Okay, now question 3. I'm really going to try not to determine the answer. A car traveling at a speed of 30 meters per second on a straight road. What would the speed be of the car in kilometers per hour? Now, we actually didn't do the conversion, but we did do the conversion of meters per second to kilometers per hour in the energy video. So let's just quickly do that again. I'm going to do it here. So if I have 30 meters per second, I'm going to do it long way because I can't remember what if I'm supposed to times or multiply. So in 60 seconds, I have 1 minute. And in 60 minutes, I have 1 hour. So what I've done now, I have cancelled my seconds and I've cancelled my minutes and I'm left with my hours. That's exactly what I want. And then to sort out the meters, in 1,000 meters, I have 1 kilometer. So the M and the M cancels and the kilometer is what's left over. So in this instance, I'm going to take the 30 and I'm going to multiply it with 60 squared divided by 1,000, or 3.6. I'm not going to do that now. We'll come back. Which one of the following pairs of physical quantities consists of one scalar and one vector quantity? Now, what I would actually do here is I will take my yellow highlighter and just highlight all the vectors. Acceleration is a vector. Displacement is a vector, velocity is a vector, velocity is a vector, and acceleration is a vector. So I'm not worrying about the pairs per se, I'm just worrying about who they are. And then distance, speed, and speed are all scalars. Which one of the following physical quantities is a vector? So we have distance, let's just do the same thing. Distance is a scalar. Mass is in kilograms, that's a scalar. Time is in seconds, that's a scalar. Displacement is your vector over there. Now, in the equation that looks like that, they ask the SI unit for AT. Okay, so we have A times T. A, your acceleration, the SI unit for acceleration is meters per second square. And time is in seconds. Okay, so we can multiply the numbers of acceleration and time, or we can multiply the SI units. So if I multiply the SI units, this S and one of the S's there at the bottom cancels. So what I'm left with is meters per second. We'll come back. Which one of the following combinations include two scalar quantities and one vector? So we're going to do the same. Yellow is vector. Displacement is a vector. Acceleration is a vector. Velocity is a vector. Force is a vector. So again, it's more like grade 11 work. Acceleration is a vector. Displacement is a vector. Acceleration and velocity, which means the rest are scalars. So we've got speed, distance, and mass. A car sets out from town X and travels 40 kilometers along a straight road to town Y. The driver turns around and immediately drives back to X. The whole trip takes 2 hours, and then they want to know what is the velocity. Okay, so now here we are going to use that formula that I said we're not going to use. Now they're asking for velocity, which means we need to use displacement. So if you're trying to determine a vector, you need to use vectors in order to determine it. I know time is a scalar, but because we have at least one other vector, we will be able to apply the direction. So let's just draw a little picture. So we have X and we drive towards Y, and then we turn around and we come back. So it was 40 kilometers one way and 40 kilometers other way. So if we look at this motion, we can say the distance will be 40 plus 40. And if I can remind you of our little summary, the green one will be the actual route taken. But the displacement only depends on the starting point and the end point. Now, if you look at this picture, it starts there and it ends there, which means my displacement is 0. So the difference between my starting point and my end point is 0. It's exactly the same place. So the displacement is 0. And this value is what I'm going to substitute in there. Question 4. A car is traveling at a constant speed of 54 kilometers per hour in a 40 kilometer zone. A policeman starts his car from rest just as the car passes him. The police car accelerates at 2 meters per second square until it reaches a maximum velocity of 20 meters per second. The policeman then continues driving at a constant velocity. Okay, so it sounds very complicated. We'll draw a little picture now. They asked to find the term acceleration. We know that from our little summary. And then they ask us to convert the kilometers per hour to meters per second. That we actually did roughly at one of the short form questions. Calculate the time it takes the police car to reach its maximum velocity. We're going to make a nice couple of information lists just now. Calculate which vehicle is ahead at the time calculated in 3. Okay, so we're going to use 4.3 to determine 4.4's answer. Calculate how far the police car has traveled before it catches up with the van. And write down the total time taken by the police car to catch up with the van. So it sounds all very confusing, but let's just draw our picture and make our information list and then see where we are at. So let's just look at the car. They tell us the car is driving at a constant speed. They give us the speed in kilometers per hour, but if you switch that over to meters per second, it is 15 meters per second. So the car has an initial velocity of 15 meters per second, and it has a final velocity of the same value. Okay, so this is pretty much all that we know about the car. Then we have the police car, and the police car's motion consists of 2 parts. Let's just give him a siren. So initially it starts off with a 0 velocity because they say it starts from rest. Okay. Then it accelerates at 2 meters per second until it reaches a velocity of 20 meters per second. So there's a little piece of acceleration where we know the acceleration is 2 meters per second square, and we reach a final velocity of 20 meters per second square. Okay. Then for the rest of the motion, we have an initial velocity of 20 meters per second, and there we will have a final velocity also of 20 meters per second. Okay, and we don't know anything about the time. We don't know the time here. We don't know the distance. Over here also we don't know the time, and we also don't know the distance. But we will be able to figure all that out with our formulas. Okay, so this is all that I'm going to do for now. Question 5, we are going to skip because this is an energy sum that we've already done. Question 6 is a car accelerates from rest at 15 meters per second for 2 seconds on a horizontal road. First, define the term acceleration. We've got that. Then they ask the distance, and then they ask the velocity. So this is really an easy, it's just one motion. The initial velocity is 0. The acceleration they give us is 15 meters per second square, although I won't even put the units in there. They're going to confuse me. And the half time is 2. And then eventually they ask me what is x, the distance, and what is your final velocity. And we'll just find a formula that works. Okay, so this one is almost the same as the police car from earlier. While traveling at a constant velocity of 108 kilometers per hour, the driver of a car notices a sign warning motorists to keep a safe 2-second following distance. At that instant, the car is 80 meters behind a truck that is traveling at a constant velocity of 90 kilometers per hour. So the first one, explain the meaning of the safe 2-second following distance. Calculate the safe 2-second following distance behind the truck. Now, if we just look at our little picture here, this is our truck, and we know the truck, just as in the previous example of the car, the initial velocity here is 90 kilometers per hour. 90 kilometers per hour is the same as 25 meters per second. And then the final velocity is also 25. So the truck doesn't change its speed or the velocity. And then we have the car over here, which has an initial velocity of 108 kilometers per hour. That's the same as 30 meters per second. And then they're asking us something about a 2-second following distance. And there's something about distance as well. So for now, I'm just going to say t equals 2. And then I do have a distance there, but I'm not sure where to put it at the moment. So let's just stop there for now. And I am, however, going to put the 2 there and a delta x over there. We'll come and figure it out in a second. Question 9. An impatient man paces up and down while making a phone call. He starts at his desk, walks 5 meters east, and then walks 7 meters west. The process takes him 20 seconds. Now, 9.1. Use a vector scale diagram and represent the 2 displacements of the man from A to B and from B to C. Label all the vectors clearly. Write down the displacement next to the vectors and then use a scale of 1 centimeter to 1 meter. So if we just take the motion that they talk about and draw it quickly, we can come back later and just do it to scale. So they tell us he starts at his desk from A, and then he walks 5 meters to B, and then he walks west, which is the opposite direction, that is B, to C, and that is 7 meters. So north, east, south, west. I just want to do a sanity check. So 5 meters east, turns around, and then 7 meters west. What is the man's change in position relative to A? Calculate the total distance the man covers. So we've sort of already done that. That's like 5 plus 7. Because distance, remember, is the green one, the actual route taken. Explain why the value calculated in 2 differs from the one calculated in 3. We'll get to that, but that's just the difference between displacement and distance. and then define the term velocity, and then calculate the man's average velocity for 4 marks, and then we're done. Right. I can just maybe come back. The average velocity, because they don't give us anything else. They don't give us acceleration, and they don't give us like initial and final velocity. So when they give you so little information, and because they use the word average, we are going to use this formula. And because they're asking for velocity, we need to use displacement there. Because velocity is a vector, so we have to use displacement, which is also a vector. And they sort of remind you there that you need to use displacement. And also, this formula is also the definition of velocity. So we've got everything covered there. Question 10. A taxi is traveling at a speed of 25 meters per second when a traffic light 40 meters ahead changes to red. Define the term acceleration. The driver takes 1 second to react before he slams on the brakes. The taxi then stops within 2 seconds. Is the velocity and acceleration of the braking in the same direction as it moves toward the light? And then give a reason for your answer. Calculate the distance the taxi travels during the reaction time. And then will the taxi stop at the traffic light? Show all calculations. So this taxi has 2 parts to its motion. So we have the reaction time where we have an initial velocity of 25. We have a reaction time of 1 second. Our final velocity is also 25 because in that 1 second he hasn't done anything yet. He's only just registering that something's up. We're not exactly sure about the distance. We do know that the acceleration is 0 because he hasn't done anything yet. If we look at the second part of the motion, that's when he actually applies the brakes. So here our initial velocity will be 25. The traffic light is red, so we want him to stop. We do not know the distance yet, but we know the total distance is 40 meters. So if we can determine this little distance here that he traveled while he was still reacting, then we'll be able to determine that value. And then A we also don't have, and T we also, T we have, that's 2 seconds over there. All right, so this is my information list. I will come back later. Okay, so question 11. I haven't really done any experiments with you guys. So this is just a little reminder of how experiments work and the different terms that we use. So they just talk here about, they're doing tests on cars, and then the information that we collect is time and position. They ask, give the correct term for change of position per unit time. Okay, so change of position per unit time. Then they want to know what is the independent variable and what is the dependent variable, and these are notes that I would actually make myself. The independent variable is the one I choose. I choose that. And the dependent one is the one that I measure. And usually the independent one is time. Not always, but most of the time the independent one is time. Use the information in the table above to draw accurate position time graph on graph paper. So they just ask you to draw it. We're going to have time there. This will be your independent variable. And this will be your position. Let's make it D, or you can make it X. And you're just going to plot little dots. And then they ask calculate the gradient of the graph. Now, we didn't get to graphs with kinematics. And it is not a crisis for those of you who are taking physics next year. You're only going to need it in grade 12, and then you sort of do it from scratch anyway. But if you take the position time graph and you measure or determine the gradient, your gradient will be the same as your velocity. But that is not important for now. Okay, so we have read through the paper. We have answered most of the short form questions. I've been busy for 35 minutes. Let's see if we can finish this paper in less than 2 hours. Okay, so if we look at question 4. Question 4 freaks me out a little bit because I've got a whole lot of information and there's different parts to this motion and it looks just very democard. So just for my own sanity's sake, I am going to start at question 6, which is nice and easy and uncomplicated. I just need my formulas that I'm going to stick up there. And because I already made my information list earlier, it's really as simple as finding the correct formula to use. So I have my initial velocity. So there's the initial velocity, there's the initial velocity, there and there. Okay, I have acceleration, that's there, there and there. I have time, that is there, there and there. This highlighter is really too big. There's also time. And now the first thing they ask is distance. So distance is x. I've got an x there and I've got an x there. So if you look at your formulas, we can only use the first formula. So I'm looking for the green one and I have all the yellow ones. The second equation does have an x, but I don't have all the other variables. I don't have my final velocity. Okay. The third one doesn't even have an x in, and the third one I also can't use because I don't have the final velocity. So for 6.2, it's going to be delta x equals vit plus a half at squared. So this means the initial velocity times, you can put in a dot if you want. So the initial velocity times time plus times the acceleration times time squared. Now I'm showing my substitution. So it's 0 times 2. So I know 0 times 2 is 0, but show the substitution. Acceleration is 15. And then we have time square. And now I have an answer of 30 meters. Now, with kinematics, it is really important to make sure about direction because we are working with vectors and scalars. So let's just read the question again. They say a car accelerates from rest at 15 meters per second for 2 seconds on a horizontal road. Okay, so it means that our movement is from left to right and our acceleration is also from left to right. So we can just work with a positive sign. And if we look at our answer, it says that it moved 30 meters in the first 2 seconds. So 30 meters in 2 seconds when I accelerate sort of makes sense. So I feel okay about the answer. And for 6.3 is what is the velocity of the car. Now I am looking for VF. So there's a VF, there's a VF, and there's a VF. And I have my delta x's now. And what I'm going to do is I'm going to use the third formula. Now the reason why I'm using the third formula is I am going to try not to use my own answers. So I could have used the second formula. You won't be wrong unless 6.2's answer is wrong. So whenever possible, try not to use your own answers, but sometimes you won't have a choice. And just maybe to show you that you will eventually get to the same answers, let's do both. So VF equals VI plus A times T. VI is 0. My acceleration is 15 and my time is 2. So then I get 30 meters per second. Okay, so I know we have got 30 meters and 30 meters per second. It won't always be the case. If I use the second formula, VF square equals VI square plus 2A delta X. VI is 0 according to my information list. Acceleration is 15 and my displacement, my distance, is 30. And then I get a value of 900, but that is still VF square. So if I draw the root there, I get 30 meters per second again. Okay, and I would actually do that in the exam if I had time. If there are 2 formulas and both will work, I will determine both of them just to sort of double check myself. You might not have the time during the exam, but do it while you're practicing. Okay, so the definition of acceleration we had when we did the summary, so you can just look at that again, but it is contained in this formula. So it is the rate of change of velocity. And then to determine the distance, this was this formula, and 6.3 is the velocity. And you don't really have a choice. So as long as you make your information list and you let your information list talk to your formulas, then it sort of tells you what to do. Okay, so that was a nice quick 8 marks. So we had almost 10 minutes to do this, and we are just past the 5-minute mark now, according to my timer. Okay, this one, question 7, was something about the 2-second following distance. It looks a little bit complicated. Let's just leave that for a second. Let's do question 9, and then we can start with question 10 and then go back to that really difficult one that we had earlier. Okay. I will do question 9.1 in a second. So this is my rough work. I just need to change it over into like meters and centimeters. So that's not a big crisis. At 9.2, they ask, what is the man's change in position at C relative to A? So they're asking, if I stand at A, where will C be? Okay, so from A, we went 5 meters east, and then we came 7 meters to the west, which means that this distance between C and A is 2 meters, right? So this is what we call the displacement, because the displacement is the difference between the initial and final position. So the man's change in position at C relative to A will be 2 meters to the west. Okay, so if I stand at A and I look towards C, C is 2 meters away from me and is to the west. 9.3 asks, calculate the total distance of the man. And the total distance will be the true path that he followed. Now, if I use the colors like we used it in our little summary, where we said vectors are yellow and scalars are green, then this is what's going on here. So our scalar is the physical path that was followed. So the man walked 5 meters and then he walked another 7 meters. And together that gives me a distance of 12 meters. But if I look at the displacement, just the change between the initial position and the final position, we have 2 meters, and then we add a direction. And that's exactly the explanation we're going to give at 9.4. Explain why the value calculated in 2 differs from the one calculated at 3. So you're going to say the value calculated at 2 is our vector, and the value that we calculated at 9.3 was our scalar, and that was our distance. And then you can maybe, just for good measure, it's only 2 marks, but for good measure I would include the definition of displacement. Displacement is the change from the initial position to the final position, where distance is the physical route traveled. Then 9.5 is to define the term velocity. So here we have it in symbol form. Velocity is the rate of change of displacement or position. And then they want us to calculate the man's average velocity. Now here you have one of 2 choices. The formula is the same, delta x over delta t. But we have 2 values now. We have a 2 and a 12. So you can either say 2 divided by 20 seconds, or you can say 12 divided by 20 seconds. Now the correct one will be this one, because they're asking for velocity. Velocity is a vector, and because velocity is a vector, we need to use the displacement, the change in position from the initial position to the final position. And then this you can just determine with your calculator. So this will be your velocity, and this one will be your speed, because you use the distance. All right, question 10. So for question 10, they tell us that a taxi is traveling at a speed of 25 meters per second, and then 40 meters ahead there's a traffic light that turns red. The first one is define the term acceleration. We've done that. They tell us the driver takes 1 second to react before he slams on the brakes. So just before we look at the actual questions, let's just go off script here and determine everything that we can, and then figure out the motion of this thing. So if we look at the first part of the motion, it is in that 1 second reaction time. So that is when the guy realizes something is going on, but his body hasn't had a chance to actually react to that information. So the initial velocity is 25, the final velocity is 25, and the time is 1. I'm curious about the displacement. So let's see what we have. So we have VI and VF. VI and VF. We have T and T and T, and we also have acceleration. The acceleration is 0. So there's nothing to determine. There's the acceleration, and there's the acceleration, and I want delta x, I am going to use the first one. So delta x equals vit plus a half at squared. Vi is 25, my time is 1. Then I've got a half. My acceleration is 0 because I haven't pressed on the brakes yet. And then time is 1 square. And then you're just going to put this into your calculator and then you get an answer of 25 meters. So if this distance is 25 meters and my total distance is 40, I have 15 meters left where I need to like press the brake and come to a standstill, preferably. The only thing here that I can determine is the acceleration. Although if we look at the question, they say the taxi stops within 2 seconds. Now I'm going to write the 15 over there because I'm not sure if this taxi will actually be able to stop in the time allocated. Let's determine if he starts with the initial velocity of 25 and he actually does come to a stop within 2 seconds. How far will he move? Okay, so we have Vi and we have Vf. We want x. We'll get to x now, and then t is there and there and there. I want x. So there's the x, and there's the x, and there's an x. I don't have my acceleration, so I can't use the first three. The only formula that I have to my disposal is the last one. So delta x equals Vf plus Vi divided by 2 times time. Vf is 0. Vi is 25. We divide it by 2. And we times it by 2. So it's 25. So with this calculation, if the guy, the taxi driver, takes 2 seconds to come to rest, we just determined that he needs 25 meters to do that. But from the moment he presses on the brakes, he only has 15 meters before he gets to the traffic light. Okay? Which means that he will only come to a stop 10 meters after the traffic light. So he's going to run the light. Okay, let's just see what questions they asked us. 10.2, they say, is the velocity and the acceleration of the braking taxi in the same direction as it moves towards the traffic light? Now, I wonder if you can remember in class, the first time I explained vectors and the direction, someone, I can't remember who now, was pushing and pulling at me. And I was pushing and, well, not pulling, pushing against the wall as well. This is the light that should come on now. If we look at the velocity of this taxi, the velocity is in the right-hand direction. Okay. If he's going to speed up, your acceleration will also be to the right. Okay. It's pushing me forwards. But now this guy is going to brake, which means the acceleration will be in the opposite direction. So when you brake, the acceleration will always be in the opposite direction of the velocity. So this is no. And here at give a reason for your answer, you can say that the taxi is driving to the right, but when the taxi brakes, the acceleration is trying to undo the velocity. So the acceleration is in the opposite direction. If you just make it clear that you understand what's going on there, you will get your marks. Okay, now 10.4, they ask calculate the distance the taxi travels during the reaction time, and we've sort of already done that. This is over here. So he travels 25 meters in the 1 second that it takes before he can make a decision. So that's 10.4. And then will the taxi stop at the traffic light? Show all your calculations, and I've already done that. So you can sort of go off script in the same way that we did with the electric circuits. You can sort of go on your own tangent and just determine everything and then come back and draw nice boxes. So this is 10.5. You can just add a little extra to say that, well, he only had 15 meters to stop, but then he used 25, so he ended up 10 meters past the traffic light. So this is why it's 5 marks. So you'll get some marks for your calculation, and then you will get some marks where you just make sense of the numbers. Okay, last question, and then we can go back to the short form ones. I think I actually answered most of them when we were doing the reading time. The first one is give the correct term for the change of position per time. So the change of position per unit time. That is your velocity. And it comes straight from your formula. All right, then we have the independent variable and the dependent variable. So the independent one is the one that you choose to use to make the measurements. So that is your time. And then the dependent one is the one that you actually measure. That is your position. And then they ask for an accurate position time graph. So you have your position on your y-axis and your time on your x-axis, and just add your labels. And this seems like it's going to be a straight line. So you're just going to make your little dots and then connect them. And obviously it's going to be nicely done on scale. Very pretty. Add your arrows. And then 11.5 is calculate the gradient. So gradient, that's pretty much just math. Your gradient is the change in the y values divided by the change in your x values. Although now we don't have y's, we actually have position. I'm going to make a D just so that's not so confusing. And then on the x-axis we have time. And you can choose any two values. Let's do these two and those two. So these will be, I'm going to call this A and B. I just need two names. So I'm going to take the D at A minus the D at B divided by the time at A minus the time at B. And now I'm just referencing. So the distance at A is 5. The distance at B is 20. And then the time at A is 1. And the time at B is 4. And here I get a value of 5. And you don't know that yet, but I'm telling you now that the unit here will be meters per second. And it should make sense because here we have meters divided by seconds. So this formula implies or tells you what the units are. Okay, short form questions, then we are done. Now question 1 we actually just sort of did just with the knowledge of our theory. We can just maybe double check them. So a vector is a small quantity and a scalar is a small quantity. We cannot say anything about the magnitude of either a scalar or a vector just by knowing it's a scalar or a vector. We just know that vectors is a quantity with a direction, where scalars only have a quantity. So this one is false. A vector quantity is described with a direction and a scalar quantity is described without a direction. That is true. That's the definition of a vector and a scalar. A scalar depends only on the initial and final values of the quantity. That is false. That is an attribute of vectors. And then distance is a scalar and displacement is a vector. That is also true. So the only one that we still need to do is 1.1, and that's actually a carryover from energy. It shouldn't be here, but let's just double check it again. So an object thrown vertically upwards, they want to know what happens to the gravitational potential energy. So here at the bottom, mgh, at the bottom we will have a 0 potential energy because we are on the ground, so our h value is 0. And then here our h value will be a maximum, whatever that is. We can make it a 10. I always like to use numbers. So there we have mgh, and that mgh value will be larger than 10 because it's mass times acceleration times 10. And here I can see I go from a value of 0 up to a value of 10. So it doesn't decrease, it increases. So this one is false. Give one word for, we already did them. So a physical quantity that has both magnitude and direction is a vector. The unit of linear acceleration is meter per second square. Displacement is a vector, so it has magnitude and direction. And a physical quantity that has magnitude but no direction is the opposite, it's a scalar. Then multiple choice questions. Here we have the 30 that we had to convert to kilometers per hour, and I did it long way, or you can just remember it. So I am going to use my calculator really quickly to say 30 times 3.6. And I get a number of 108. So my answer here is C. 3.2, they ask which of the following pairs of physical quantities consists of one scalar and one vector. And because I used my color, I want a green one and a yellow one. So the answer is B. Which one of the following quantities is a vector? That's the yellow one again. That was B. Okay, this one was the SI unit. So acceleration times time. Acceleration is meters per second square, so I can write it as a little fraction. And then time, I also can write as a fraction, seconds over 1. And when I cancel the s's, I end up with m over s, or meters per second. So my answer there is C. 3.5 is which one of the following combinations include 2 scalar quantities and 1 vector? So vectors we made yellow, and scalars we made green. So I want 2 green, 1 yellow, and just by color I can see the answer is B. Then 3.6, this was the car going from X to Y and then back to X again, and they ask us for the average velocity. So this one is almost the same as this one here, where they ask us to calculate the man's average velocity, and I told you there's 2 ways of doing it. It's either with the 2 or with the 12. We had 2 meter values, but because they are asking for the velocity, we need to use the displacement, and displacement is 0. So 0 divided by 2 hours is just 0. So our answer there is A. And there we are done. Okay, well done, guys. Make sure you have your summary of everything about kinematics. I think most of these sums in questions were quite easy, except maybe for that safe following distance one. That was a bit of a difficult one.